Okay, good morning guys. Problems, questions, observational remarks? Before I forget, tonight no lab, because it seems like everybody finished the measurements and experiments on the boost converter, so we can skip one lab session. Next week we will have a lab for the boost topology, but not tonight. What was the last subject? We're starting to talk about control of modeling of switch model converters, and the modeling of this converters requires two steps, because we have our original circuit that is a non-linear time variant system that is already a bad guy. And we want to get an LTI system, linear time invariant, so we can use all the standard techniques you learned in your studies to design that is basically Laplace transform or Z transform. In order to go from non-linear time variant to linear time invariant, we need to go through two steps. The first step is called average. And average allows us to remove the time variance, the switches. So if we average our equations, our circuits, our components, we get a non-linear time invariant system. And if we go from, if we wanted to get a linear time invariant system from a non-linear system, we need to perform a second step, that is linearization. And this will be what we will do this week, possibly next week, to find for each topology we learned, for each mode of working, CCM, DCM, and linear time invariant model, small signal model for the power system. I already started to tell you something about average. There are many of them. We will see in this class only 3 of them. And the basic idea is that if I have a vary system, I have a waveform that, for example, is something like this, I can take the average over one period. So I can average this one. And there are many different techniques to average this. I already told you one, that is, I can say that x t average equals integral from t minus this switch to this to t of x tau in the tau. This is a possible average. This is so-called moving average. That means you take a window that is this switch second long, and you move it across your signal, and you get the average. This average is a continuous function, because you take your signal, for example, a signal like this, you take your window from here to here, and you say, oh, what's the average on this interval? Then you move your interval a little bit to the right, 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 and while moving this interval as a length of the switch, you keep evaluating this average, and you get your smooth average function with this expression. We won't use this expression directly. We will use something similar to this. That is a possible technique. What you get at the end is an average function of time, continuous function. Then there is another technique. For example, you can have a signal like this. Constant frequency, just a different amplitude, duty cycle, whatever it is. You can say, okay, I average over one cycle, say from here to here, and all these, the average of all this cycle is just compressed, it's just zipped into one single number, one single value. And so you say, okay, the average is just this value. Then you say, okay, next move to the next to the following cycle. You take the average of this cycle, and that is collapsed into one number. This one. And then you do the same for this cycle, and you get something like That means each cycle is just reduced to one single number. What you get at the end is an average, because you average each single cycle, but it's not a continuous function, it's a discrete function. A function is a sequence of numbers. So you could also define an average like this: x of n is which, that is something discrete, equals, this is the average value, is the compressed value, equals 1 over this switch integral from n minus 1 this switch up to n this switch of x tau tau by d tau. This is another technique. Instead of working with our function, continuous time function with the jumps and discontinuities and things like this, we just compress one cycle in one number. So what we get after this kind of average, we have a sequence of numbers. And you could use, for example, the standard discrete tools that you have for discrete systems. What do you know for discrete systems? What is the basic mathematical tool to deal with time discrete systems? Z transform. So you use Z transform and you have this stuff. Actually, you cannot use Z transform directly on this sequence of numbers because you have first to check if the system is linear or not. But once that you linearize it, this is a Z transform system. If you want to control your microprocessor, your converter with a microprocessor, probably that is a good approach. Not easy to use, but it's a good approach. We will stay in continuous time domain. We will stay on that other side. That means our average will be a time continuous average. And I told you there are many different techniques to average converter. And let's start with the very first, historically was the first used, is the state space average. And the basic idea is this. Let's consider a converter. Let's take, for example, a boost converter. Why not a buck converter? Because a buck converter is too easy. We will use it in another case. And the boost converter in CCM is something like this. Big in switch diode. Oh, you know how boost converter is. Boost converter in CCM has two stages, two configurations. One is when the switch is closed, and if the switch is closed, the schematic we get when the closed switch is just this one and this one. This is during T on, that is equal to D times the switch interval. And when the switch opens, and we are in CCM, which is the only other possible state, the switch opens, diode conducts, and my circuit becomes something like this. Is this a linear circuit? Yes. Is it a time invariant circuit, this one? Yes, this is a stupid circuit that you could learn to solve in circuit theory many, many years ago. What about this circuit? Is it time invariant? Just this one, don't look at anything else. Yeah, this is time invariant. And is it linear? Yes, it is linear. Unfortunately, this situation does not last forever. It only lasts for a time t of equals 1 minus d times the switch. So, if my circuit is just this one, piece of cake to solve. If my circuit is just this one piece of cake to solve. But if my circuit is a converter, this converter stays for a while with these schematics, then the schematics changes, becomes this one. And then it changes again, becomes this one. So we have this bouncing forward and back between these two configurations. But each single configuration that lasts for a time t on, that lasts for a time t off, is a linear time invariant system. So we can use all the standard techniques that you learned in circuit theory to describe these two circuits. And one standard technique is to write down the differential equations for these two circuits using the state space technique. Do you remember state space? Say yes. Yeah. Is it a real yes or just to make me happy? Okay. If you have to describe a dynamic system, linear time invariant dynamic system, and each of those two circuits are linear and time invariant. Unfortunately, they don't last too long. If you have to describe a linear time invariant dynamic system, the basic equations using the state space technique is to write down something like that. X dot equals ax plus du. Yeah? Something new over here? No. And possibly something like y equals cx plus du. Everything is clear in these equations? What's x? State vector. What is inside the state vector? There are the state variables. What are the state variables in our circuit? Current to the inductor and voltage across the capacitor. What is A? Mathematically speaking. Matrix, describing the topology and the components that are in my circuit. What is U? Input, forcing input. What is B? Well, B is a factor, is a matrix that describes how these U are applied to my circuit. What is Y? Output. Output vector. We can have many outputs. In this case, we will consider only one, that will be our output voltage. C is a matrix, D is another matrix, X and U are still the same. What are the eigenvalues of A?
Polynomial characteristic polynomial.
That's a characteristic polynomial, yes. What is that? What does it mean, characteristic polynomial? That's true.
That describes
what are the roots of this characteristic polynomial that is the eigenvalue? Poles of your dynamic system. So, just looking at this A matrix, we can have an idea, we can evaluate, we can find out what are the poles of my dynamic system. Okay? So, we can write down this equation for each of our two initial circuits. Because this is time invariant linear. Unfortunately, it lasts only 3 microseconds. This is time invariant linear. Unfortunately, it lasts only 4 microseconds. But okay, the map that we can do about it. So let's call it LC. You told me that state R, state variables are the current to IL, current to inductor, and the voltage across DC, across the resistance. And we are lucky because the voltage across the capacitor. We are lucky because the voltage across the capacitor is also the voltage across the output resistance. So the voltage across the capacitor is also my output voltage. I don't need the Y equation, Y equals Cx plus du, because my output is already a state variable. So if I find the state variable, I also find my output. And here the same story. IL, LC, DC, R, and this is within. Do you know a technique to write down quickly the state equations for these two circuits? What we'll do this morning is, unless you have a better idea, I write down this normal equation over here for these two circuits. I transform them, I write them back into matrix equation, And then when we needed to make a calculation on this equation, we have to go back to the standard form. That means di by dt equals, or dv by dt equals blah, 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 blah. Not in the matrix equation. But I want to pass through the matrix because I know that the formulation that is important. So, let's start to write down the differential equation for this circuit. That's easy because we have the standard way that I use to write down this equation is to write here L dIL by dt, and here C dVC by dt equals, and then we have to write here the voltage across the inductance, and here the current through the capacitor. And the voltage across the inductance over here is just V. So this is V in, and here the current through the capacitor is equal to, the rules to write down the state space equation is that on the right hand side you can only use the state variables or the inputs, nothing else. So C dVC by dt, that is the current to the capacitor. The current goes into the capacitor because I use the user load sign convention. C times dVC by dt is the current going into the capacitor is equal to what? Negative Vc over or V naught over R. Vc and V naught are the same. So this is equal to negative Vc over R. Yeah, okay, those are the first two differential equations. Well, it's complicated. Today is the only time that I use differential equations. Then that will be over and we will forget them. No, you don't have to forget them, at least for this. And here's the same story. L dIL by dt C dVC by dt equals voltage across the inductance. How much is the voltage across the inductance over here?
V
minus Vc. And what about here? Current going into the capacitor.
I input minus I output.
Is IL, inductor current that goes to the right, minus what is going to the load. It is minus Vc over R. Yeah, okay, well. Now it's just a simple, stupid, boring algebra for a while. And the simple, stupid, boring algebra tells me that because I want to go to the standard matrix formulation, dIL by dt equals V in of L dVc by dt equals negative Vc over Rc, and those are the first two equations. And here I have the second bit, that is dIL by dt equals V in minus Vc over L, and here dVc by dt equals IL over C minus Vc over Rc. So far so good. You have here on the left hand side the derivatives, on the right hand side everything else, and so writing down the matrices is a piece of cake right now. It's not really needed to write down the matrices, but useful. So we have here my state vector, the derivative of the state vector. That is, let me write here like this. IL dot, I put a large dot on top to indicate the derivative. It's not just the dot of the I letter. It's a big dot indicating the derivative. Don't ask me to write down the derivative over here because it becomes smaller and smaller on my phone. And here we have Vc dot equals our A matrix. What's our A matrix? Plus A matrix times the vector, that is I add VC plus B matrix, in this case is B vector, times U. U is the input. What's the input over here?
V in and U, no V.
V, just times V in. If your load was not just a resistor, but if your load was a resistor plus current sink, that means general linear network, an equivalent network, non-equivalent network. In this case, here beside the VE, you have to add I naught. I naught becomes an input. Even if, or I add whatever it is, this I naught, whatever it is, this current. And in this case, this current, the power-wise is the current going to the load, is your output, your converter output. For the control point, from the control point of view, this output is an input, is something that goes into your differential equations as a forcing term. But we won't consider this for today. And even so, what is inside this matrix? Tell me what are the coefficients, the terms in this matrix. You have the equation over there. Here is I dot as a function of IL. 0. Here is I dot as a function of BC. Oh, I like zeros in a matrix. Here is V dot as a function of IL, that is great. Let's hope that it's not a 0 here, otherwise that's useless. What do we have over here? VC dot, V dot as a function of B.
Minus 1 over
Negative 1 over RC. What do we have over here? For the forcing term, the input term.
1 over L. 1 over
1 over L, and here 0. Okay, that's the first equation. This is my X dot, this is my A, this is my X, this is my B, and this is my U. Exactly the standard way. And then we have to do the same for the second equation. And for the second equation, we get, oh, we have please on my double check my algebra because I want to have a very terrible headache, so it's very possible that I forget terms, so I add apples and oranges together. Second equation for the second term, I dot, big dot, VC dot equals matrix times ILVC plus the B vector, the B matrix, in this case it's just a vector, times VA. Remember that if we had also I naught, that would be a matrix, and VA and I naught would be a vector. Let's say this A matrix. What do we have over here? Just look at these equations. 0. What about here?
Negative 1 over L.
Negative 1 over L.
1 over C.
1 over C.
Negative 1 over RC.
Negative 1 over RC.
1 over L.
1 over L. 0. That is the standard differential equation for a linear time invariant system. That is my Boost converter during T off. And unfortunately, my Boost converter stays in T off state only for a few microseconds. Then it switches back to the previous one. So, if you want to use these equations, this one and this one, to solve your circuit, you can do it. That means you start with your initial equation, initial conditions, you apply this, you solve these differential equations for a time that is just T on. After T on, your initial values for I and N has changed. These initial values have been transformed into the final value for T on. You take these final values at the end of T on, and you use them as initial values for these equations. And you solve this equation, you go with this equation for a time that is t off, for a period of time that is t off. These initial values are changed by this transformation, by this operator, and you get IL and BC at the end of t off. What do you do at the end of t off? Use these final values as initial values for this set of equations. And you start to going forth and back, forth and back, forth and back, and you become old, very old, because this is a very time-consuming calculations. Those are basically just solving differential equations step by step. Everything okay up to this point? We can write this equation as x dot equals a2 times x plus b2 times u, and we can write this equation not like an a, but a1, because this is the first state and this is the second state, so I just need to make very clear that a1, a during this state and a during the other state are different. So, if you want to have a MATLAB working hard for you, you can just give it these two equations, these two matrices, and having MATLAB to solve it. That's okay. You become old. And you don't get any linear time invariant system. What happens is that Professor Middlebrook, many years ago, while trying to solve this problem, you remember that I told you the story last time, while trying to solve this problem, he came out with this idea. Probably he got a triple McBurger one evening, so he had a very nightmare night, and he came out with this idea. And the idea is, these equations are valid, hold true, for a period of time that is a fraction of time that is just a t. These equations just last for a period of time that is d. Fraction of time. Period of time is d times this width. These equations with A2 matrix, with B2 matrix, are valid for a fraction of time that is 1 minus d. So if I have two equations, I could think to make an average of these two equations, this equation and this equation, and sum them together, add them together, with a weight that is 1 minus d for the equation during t off, and d for the equation during t off. You have to admit that it's a very strange idea, because you say, okay, my system is bouncing forth and back between two equations that are x dot equals a1 x plus b1 u, or x dot equals a2 x plus b2 u. This lasts for a period of time, for a fraction of time, not a period of time. Fraction of time d, this is 1 minus d. I just multiply this equation by d, I multiply this equation by 1 minus d, and I add them together. What do I get? I get, when I multiply by d, I get something like x dot that multiplies d plus x dot that multiplies 1 minus d. Just like x dot. X dot equals a1d plus a2 times 1 minus d x plus b1d plus b2 times 1 minus d times u. And he claimed that this average equation represents the average behavior of my circuit. We will see in a moment if it is true or not. Well, it is true, otherwise I won't wait for this time. Under what conditions these equations are true. I just average these two equations. I multiply the first by t, the second by 1 minus d, and I add them together. It was a triple McBurger for sure, with extra size fries, because it's not standard idea that you can have. Before going any further, let's just see what is the meaning of taking an average. Not only this average, any average. If you use these two equations and you bounce forth and back from this equation to the second, and then back to the first, and back to the second, etc. You solve your circuit for all points in time. What you get from the solution of these two equations one at a time, first this one, then this one, and so on, are all the waveforms in your circuit. Once that you average it, you are starting to lose information. Because everything that happens inside one cycle just disappears. Let's say, if you have this waveform and you average it, this waveform is transformed into function that is not has not this shape anymore. Or even worse, if you go to the discrete time, this function is just reduced to a single point, a single value. So what do we lose going from the original system to the average system? Well, we lose everything that happens inside one cycle. We lose the peak values. Are not there anymore. We lose the RMS values. We lose the instantaneous values. What are we left with? The only quantity from the original system that we keep after averaging is the average. We still have the average voltages, the average current, but not the waveforms, not the shapes, not the peak values, not the RMS values, just the average. Okay, this is important. Let's see the same phenomenon that we lose information from a different point of view. Let's go to the discrete time for a moment. If we compress, if we collapse all this information in one number, then the other waveform here in another number over here. We have just one number each discrete seconds. We have a sampled system. And if you have a sampled system, what do you lose in a sampled system? Or what can you represent in a sample system? Sampling theorem, tells you something. Nyquist. Poor guy, Nyquist, was not Nyquist. His name was Nyquist. He was Swedish. Then moved to the United States, and his name became Nyquist because everybody was able to call him Nyquist. Exactly like when I am in the United States, I am Medalino, or something like this. Anyway. What does the Nyquist sampling theorem tell me?
We have to double the frequency of the signal.
We have to double the frequency, at least the sampling frequency, if we wanted to see some phenomenon with a given bandwidth. But this is the other way around, because my frequency is fixed. My frequency, my sampling frequency, is 1 over switching frequency. Sorry. 1 over this frequency is my switching frequency, is my sampling frequency, is also the switching frequency. This F switch. This is fixed. We decided it at the very beginning of our design. So, all the information we can have in frequency domain will be only up to 1/2 of this switching frequency. So, if my switching converter works at 200 kilohertz, I cannot see any phenomena that is above 100 kilohertz in my system. That is more than enough. So, when I average, I lose information on everything that happens inside the cycle. I lose waveforms, I lose peak values, I lose RMS values, I only keep average values. And from frequency point of view, frequency-wise, I just see what happens up to 1/2 of the switching frequency. Above that frequency, 1/2 switching frequency, there is uncharted land. We don't know what happens. Okay? So far so good?
Professor, a question.
Yeah.
Why we can't monitor the system in a frequency higher than F switch? We can't drive the system with a frequency higher than F switch. But we can measure the system with the frequency higher.
We could have signals, the question is, we could have signals in our systems that are higher than the switching frequency. For example, the input voltage could have a frequency in it, a noise, above it, that is higher than the half of the switching frequency. Yes, it's true. Or we could, that's all what we can do. What happens? Well, what happens if you have noise that is above the Nyquist frequency? What's the phenomenon occurring if you have a signal that is more than one half of the switching frequency? Aliasing. Yes, we will have aliasing, and it's not common because at the input of our switch model converters there is a big capacitor, so you cannot inject high frequency noise in it. But we will have one case and show you that we have aliasing. I will forget probably to tell you that it's aliasing, but it will be aliasing. What about duty cycle? And duty cycle is intrinsically, even if for us duty cycle is a number that goes from 0 to 1, intrinsically duty cycle is sample because it's just the T ohm of the switch. And if we change the duty cycle, nothing happens till the next cycle. So it's already a quantized quantity, a sample quantity, not quantized. Okay, did I answer? It's possible, in one case we will see aliasing, in the other case duty cycle cannot change. Oh, before going any further, I want to point out two things. First, I am not using the standard convention of capital letters and lowercase letters for variables, constant, etc. If somebody took the class of circuit electronics with me, I use a different convention. This is the convention that is used in power electronics. Everybody in power electronics, every book you read has this convention, so I will sticking to it. Second point, before going any further, I am not so sure that this is really true. So let's try to see in a simple example if this is reasonable or not. So let's consider for a moment, before going to solve the equation, because I want to solve those equations, let's consider for a moment if this is reasonable or not. If I can apply this method to a simple system and see if it works or not. And my simple system is a system just the first order linear without a forcing term, without a mid term. That is something like this. X dot equals A1 X, and this lasts for a time that is D times the switch. And then the system changes A1 factor. And so I get a different system that is X dot equals A2 X, and this lasts for 1 minus B by 2 switch. I am doing the same things that I told you over there, but in a simple system that has no U term, that has only one scalar factor, not a matrix, so I don't have to write too many things. And you know what is the solution for this differential equation? What is the solution for that differential equation?
Exponential.
It's an exponential. I have here xt, in general, for this kind of equations, solution is xt equals
Exponential of minus.
No, it's not minus. It's there is an error in English notes. There is a negative sign. There is no negative sign. I put a negative sign probably during my lecture because I have used it. Every time you see an exponential in electronics is e to the minus something. Well, mathematically speaking, if a2 is positive, it means that this is positive. E to the a t. One thing missing.
Constant.
No.
AT over tau.
Tau is 1 over a.
Initial condition.
Yes. X0. Tau. Come on. X0 times e to the at. This is the differential, the solution of the differential equation. X dot equals ax. Just as a reference, I need it because I need it to apply it twice. And I have here then. Let's solve it for a period of time that is this switch, dt switch for t ohm. So x at d times this switch will be equal to what? To x0, the initial condition, times I just want to find out how much is x at time d switch. I am not interested in the exponential solution. I just want to know what is the final value at this interval of time, so I can use it as an initial value to the next period of time. X, my variable, at the time d switch, that means at the end of this period of time, is equal to x0, the initial condition, times e to the a1 times data switch. And if I want to find out how much is x at the end of my complete cycle, that means how much is x at the time to switch, that means after one cycle what happens, I write it, that will be e to the a2 times not the switch, because this second differential equation does not start from 0, it starts from dt switch. So this time is just the length of time, the period of time, while this equation is valid, it's true. And this is just the t off. That is, it will be 1 minus d switch. And what is the initial condition of this second differential equation?
The final condition of the previous one.
Is x0 times e a1 d switch times, and this is an operator that takes my initial condition and transforms it in the final value after one cycle. Possible? Please observe that it's not needed to start exactly at the beginning of a cycle. If this is your cycle, from here to here, and you want to solve it for a more complicated case, starting from here, you apply first the d, and then 1 minus d transformation. If you start from that point, that's okay. You will have one fraction of the equation d, then you have the equation 1 from 1 minus d, and then you have another piece of cycle of kind of the equation for d. So you still have the equation that lasts for d time, and the 1 minus d equation that lasts for 1 minus d. So it's not important where you start. It's just convenient to start from 0, but it's not important. This is not a sampled system. This is a continuous time system. So this is equal to x0 that multiplies e2 a1 d plus a2 1 minus d times the switch. That means after one cycle, no matter where you start, I started for convenience from 0, but you can start from any point. The final value after one period of time, one switch period, is this switch that multiplies this expression. What is this expression? This is just a time constant, the reciprocal of a time constant. This is just a new A average. And this A average, you see, this kind of coefficient, this A average is just A1 multiplied times D plus A2 multiplied by 1 minus D. And the same thing this is exactly what I did, what Professor Linearization did for the complicated problem. This is a complicated problem, but it's exactly the same. Instead of seeing a single reciprocal time constant, a single coefficient A1 and 2, lowercase, we have here two matrices. But if you observe, we have exactly, this is our new A, equivalent A time constant, what we did over there, that is A1 times D plus A2 times 1 minus D. We find Never a time constant that is the average of the two coefficients, derived from the two coefficients. It's not a time constant, neither the lowercase, neither nor the uppercase. But this is the solution. Is it true? Does it work? Is it convincing this? Bad news, guys, this is wrong. What I did over here for the scalar case is right, this is wrong. Those are the mysteries of mathematics if you study it, but if you study it, it's not quite obvious that this is wrong. Because let's consider the same stuff over here. The solution should be something like e to the a1, e1, the switch, times e to the matrix a2 that multiplies 1 minus b, the switch, equal to e to the a1 d plus a2 1 minus b, the switch. This is not right. This is badly wrong. This works, this inequality, this property of exponentials functions, exponential function, that is, for the exponential function, e to the a times e to the b equals e to the a plus b is only valid for scalars, for numbers. It's not valid for matrices. This is wrong. It's not equal. Because you know how to exponentiate a matrix. You know how to find e to a1b or e to the a1 matrix. This is a matrix. You know how to find this matrix. This is a solution, this is exponential.
Going to the eigenvalues base. Going to the eigenvalues base.
Eigenvalues basis, yes. So you have a decomposition in singular values with the two matrices. I don't remember how you call it, p times a times p to the minus 1 or something like this. That is a possibility, sure. One more.
If matrix is diagonal, we can simply...
You are cheating if the matrix is diagonal. Our matrices are not diagonal. You are right, it's the same method is suggested. One more. Taylor. Don't try this at home, but you can say that this is e to the matrix, expand the exponential in Taylor series, and you get the result. But let's see what happens over here. Here we have e to the a1 times e to the a2. This is a matrix. Let's call this matrix C1 times matrix C2. And you write wrongly that this is equal to a1 plus e to the a1 plus a2. This is wrong. It is wrong. It's very easy to see why it's wrong. Because if you exchange a1 and a2, swap these, you get here c2 times c1. What's the property of the matrix product?
We cannot swap.
It's not commutative, it's not available. So you cannot swap the two terms. If you exchange here a1 and a2, what you get here is c2 times c1. And these two products are different because matrices have this property. What about if you exchange here a1 plus a2? You get a2 plus a1, so you still get the same result. So you have this proof that this result is wrong because you write that a e to the a1 times e to the a2 equals possibly. This one equals possibly to e to a2 times e to a1. And you know that these two are not the same because those are two matrices. Too bad, guys. This method works for scalar, does not work for matrices. But there is, we are lucky because in this case it works. Even if mathematically speaking it's wrong, for this case it works because let's consider e to the a1b discrete. He expanded in Taylor series, and what do we get? What is the expansion of an exponential?
1 plus.
1 plus that, we cannot write here 1, we have to write here identity matrix, that is I, big I, plus this A1 bit discrete, plus